Welcome to Principles of Ecology. Today, we are diving into a fascinating and deeply important topic, restoration ecology. Imagine having the power to bring a dead, barren wasteland back to life. That is exactly what this field is all about. We will explore how scientists act as ecological doctors, using both biology and mathematics to heal our planet's most damaged ecosystems. Let us get started. To understand restoration ecology, start by imagining a person who has suffered a severe physical injury, like a broken bone. While the human body has a natural ability to heal minor scrapes, a severe injury requires a doctor to step in, set the bone, and provide medicine. Nature works in a very similar way. When an ecosystem gets severely injured by extreme human activities like strip mining, massive deforestation, or toxic chemical spills, it cannot simply heal itself if left alone. It is too broken. It needs an ecological doctor to step in and provide the right conditions for recovery. Now that we understand the need for an ecological doctor, let us formally define what this means. Restoration ecology is the scientific study that guides the practice of ecological restoration. Ecological restoration itself is the active process of assisting the recovery of an ecosystem that has been degraded, damaged, or destroyed. Think of it as reverse engineering a highly complex biological machine. We are not just planting a few trees and walking away. We are actively rebuilding the intricate webs of life, combining biology, chemistry, and earth sciences to reconstruct the environment from the ground up. Before we can fix a broken machine, we must know what it looked like when it was working perfectly. In restoration ecology, scientists must first deeply understand the original, untouched ecosystem. We call this original condition the reference state. Once we know our target reference state, we can figure out the exact biological and physical steps required to get back there. This hands-on process involves reintroducing native plant and animal species, rebuilding depleted soil nutrients, and restoring natural water flows. Every action is a deliberate step toward that original, healthy reference state. You might be wondering, why does this field matter so much in our modern, industrialized world? The simple truth is that human civilization relies entirely on the services that healthy ecosystems provide for free. These life-sustaining services include filtering our drinking water, pollinating our food crops, and absorbing climate-warming carbon dioxide. When we destroy a forest or drain a wetland, we lose these vital services, which directly puts our own survival at risk. Restoration ecology is not just about saving nature for nature's sake, it is about preserving the very systems that keep humanity alive. Building on the importance of ecosystem services, let us consider the cost of doing nothing. If we did not have the science of restoration ecology, millions of acres of abandoned mines and clear-cut forests would remain barren wastelands forever. This would lead to massive local extinctions and eventual environmental collapse. By actively restoring these degraded areas, we bring back vital biodiversity. Furthermore, growing new, carbon-absorbing plants helps us actively fight climate change. Ultimately, restoration ecology is our best tool for securing a healthier, more stable planet for all future generations. Now that we understand the goals of restoration, how do we actually know if our efforts are working? Ecologists need to measure the ecosystem's recovery over time with high accuracy. We cannot just look at a growing forest and guess if it is healthy. We need rigorous mathematical models to track our progress toward that ultimate reference state. These models help us predict how an ecosystem's health, such as the number of native species or total plant biomass, will grow over time and eventually level off as it reaches its fully restored natural condition. This brings us to the mathematical heart of restoration ecology, the asymptotic recovery equation. Conceptually, this formula describes a system that grows quickly at first, but slows down as it approaches a maximum limit. Let us look at the symbols. R of t represents the recovery level of the ecosystem at any given time t. REQ stands for the equilibrium state, which is our ultimate target health. The constant e is the base of the natural logarithm. The variable k is the recovery rate constant. A larger k means the ecosystem is healing faster. Finally, t is the time elapsed in years. As time increases, the ecosystem's health gets closer and closer to the target equilibrium. Let us see this formula in action with a concrete example. Imagine a mining company destroyed a rainforest, leaving 0 native plants. We are given a target equilibrium of 120 species, a recovery rate of 0.1 per year, and we want to find the recovery after 10 years. We plug these exact values into our equation. Multiplying the rate and time gives us an exponent of -1. The exponential term evaluates to approximately 0.368, meaning 36.8% of the ecosystem is still missing. Subtracting this from 1 shows we have reached 63.2% recovery. Multiplying by our target gives us about 76 native plant species thriving after a decade. Now, let us look at a different scenario where we need to find the time required to reach a specific goal. A degraded wetland needs to recover 90% of its biomass to filter water properly. We are given a current recovery target of 450 kilograms, an equilibrium of 500, and a rate of 0.05. We set up the equation and divide both sides by 500 to get 0.90. Rearranging the equation isolates the exponential term, giving us 0.10. To get the time variable out of the exponent, we take the natural logarithm of both sides. Finally, dividing by the negative rate constant reveals it will take approximately 46 years to reach our functional threshold. Having calculated these values, let us visualize what this mathematical model actually looks like. Here, we have the asymptotic ecosystem recovery curve. On the horizontal axis, we have the time elapsed since the restoration project began. On the vertical axis, we measure the ecosystem's recovery, such as species richness. Notice the dashed horizontal line at the top? This represents our reference state, the ultimate equilibrium target. The solid curve starts at 0 and rises steeply at first, showing rapid initial healing. But as time goes on, the curve flattens out, getting closer and closer to the reference state without ever quite crossing it. This perfectly illustrates how recovery slows down as the ecosystem matures. The diagram and our previous calculations reveal a vital, humbling lesson about restoration ecology. In our wetland example, it took nearly half a century just to reach 90% recovery. While human actions, like deforestation or chemical spills, can destroy a complex ecosystem in a matter of days, restoring it to full health is an incredibly slow process. It is a multi-generational effort that requires immense patience and long-term commitment. We cannot rush nature. We can only provide the optimal conditions and allow the mathematical reality of biological growth to take its course over decades. We have covered a lot of ground today, so let us review our key takeaways. First, restoration ecology is the vital science of actively repairing ecosystems that human activities have degraded. Second, all restoration efforts are guided by a deep understanding of the original reference state. Third, we use mathematical models, specifically the asymptotic recovery equation, to track progress and predict how long healing will take. Finally, remember that while reversing environmental damage is a slow process, it is our absolute best tool for bringing dead zones back to life and ensuring the Earth remains habitable for all species. Great job following along.